Hi, welcome to class. My name is Don Lafond, Professor Don, and this week in Cisco 1, we are covering Module 3, Protocols and Models. Presentation will be less than an hour, probably about 45 minutes or so. If you are with me live, hold your questions until the end of the presentation. I'll give a question and answer period. If you are watching this as a recording inside of our classroom, I want you to ask your questions inside our help discussion forum. And if you're watching this on YouTube, please ask your questions down below in the comments, and I'll be happy to answer those questions. But I also encourage other viewers of my videos to answer each other's questions. That is a perfect environment. Let's go ahead and I'm going to go ahead and share my screen. A couple things I have to set up here. I've got to move this over there. Start my presentation. We're going to start off today with a couple videos. Those videos will help you understand the internet as a whole, with at least as it pertains to routers and switches. I really like this video. It's called The Dawn of the Internet. We'll get to it in just a minute. Those videos, if they don't show up good on your screen as part of a recording, me recording a recording, the videos are available online. Either they're available on YouTube, I show the resource, or those videos are also available on itanswers.com. I gave you that reference earlier, and you can ask me for the reference of where I find these videos. If you ask, actually, I can show you, right? I can tell you, it's itexamanswers.net, itexamanswers.net, have all the videos that are inside of NetAcad, plus the content as well. So if you can't see the video, it doesn't come across well, by all means, watch the video online and you'll be able to hear it and see it better. All right, let's get to Module 3, Protocols and Models. We will explain how network protocols enable devices to access local and remote network resources. The rules will describe the types of rules that are necessary to successfully communicate. We'll talk about protocols. We'll explain why protocols are necessary in network communication. We'll talk about protocol suites, explain what the purpose of adhering to a protocol suite. We'll talk about standards organizations. Now, I actually skip over a lot of the standards organizations because if I just read them out, a bunch of acronyms and a bunch of purposes for each one of those acronyms, it's all going to blur together. So I just tell you to create some, I encourage you to create some study guides, maybe flashcards, for example, with the name of the organization on one side and the purpose on the other. That's really how you're going to learn about the different organizations that create our standards and maintain them. We'll talk about reference models. We'll explain how the TCP IP model and the OSI model are used to facilitate standardization in the communication process. We'll talk about data encapsulation, and we'll also talk about data access, explaining how hosts access local resources on a network. Rules of communication. Well, before we really get into the rules of communication, I played this video. It's the dawn of the net. It is 13 minutes. I realize it's a pretty long video to watch within another video. So if it's not a good recording, again, just pause it and go out to the internet. I'll show you the link in just a second, and you can watch this video on YouTube, maybe in a better quality than you care. It is the name of it is The Dawn of the Internet, the Dawn of the Net, How the Internet Works, and it was posted by FIU Hospitality, and this is the exact YouTube video URL. So anyways, if you need to go there, you can do that. But here I'll play this and let's learn a little bit about how routers and switches are used inside of the network, and how you as a technician as a Cisco technician will be working with routers and switches to facilitate the internet access, extranet access, and whatnot. So here we go.
For the first time in history, people and machinery are working together, realizing a dream. A uniting force that knows no geographical boundaries without regard to race, creed, or color. A new era where communication truly brings people together. This is the dawn of the net. Want to know how it works? Click here to begin your journey into the net. Now, exactly what happened when you clicked on that link? You started a flow of information. This information travels down into your own personal mailroom, where Mr. IP packages it, labels it, and sends it on its way. Each packet is limited in its size. The mailroom must decide how to divide the information and how to package it. Now, the package needs a label containing important information, such as sender's address, receiver's address, and the type of packet it is. Because this particular packet is going out onto the internet, it also gets an address for the proxy server, which has a special function, as we'll see later. The packet is now launched onto your local area network, or LAN. This network is used to connect all the local computers, routers, printers, etc. for information exchange within the physical walls of the building. The LAN is a pretty uncontrolled place, and unfortunately, accidents can happen. The highway of the LAN is packed with all types of information. These are IP packets, Novell packets, Apple Talk packets. They're going against traffic, as usual. The local router reads the address and, if necessary, lifts the packet onto another network. Ah, the router, a symbol of control in a seemingly disorganized world. There he is, systematic, uncaring, methodical, conservative, and sometimes not quite up to speed. But at least he is exact, for the most part. As the packets leave the router, they make their way into the corporate intranet and head for the router switch. A bit more efficient than the router switch plays fast and loose with IP packets, deftly routing them along their way. A digital pinball wizard, if you will. In there. Left, right. You got it. Here it comes. Right out. Heat. Oh, it's going. Hey, wait. Watch out. Here comes another one. Oh, here we go. As packets arrive at their destination, they're picked up by the network interface, ready to be sent to the next level. In this case, the proxy. The proxy is used by many companies as sort of a middleman in order to lessen the load on their internet connection, and for security reasons as well. As you can see, the packets are all of various sizes, depending upon their content. The proxy opens the packet and looks for the web address or URL. Depending upon whether the address is acceptable, the packet is sent on to the internet. There are, however, some addresses which do not meet with the approval of the proxy, that is to say, corporate or management guidelines. These are summarily dealt with. We'll have none of that. For those who make it, it's on the road again. Next up, the firewall. The corporate firewall serves two purposes. It prevents some rather nasty things from the internet from coming into the intranet, and it can also prevent sensitive corporate information from being sent out onto the internet. Once through the firewall, a router picks up the packet and places it onto a much narrower road, or bandwidth, as we say. Obviously, the road is not broad enough to take them all. Now, you might wonder what happens to all those packets which don't make it along the way. Well, when Mr. IP doesn't receive an acknowledgement that a packet has been received in due time, he simply sends a replacement packet. We are now ready to enter the world of the Internet. A spider web of interconnected networks which span our entire globe. Here, routers and switches establish links between networks. Now, the net is an entirely different environment than you'll find within the protected walls of your LAN. Out here, it's the Wild West. Plenty of space, plenty of opportunities, plenty of things to explore and places to go. Thanks to very little control and regulation, new ideas find fertile soil to push the envelope of their possibilities. But because of this freedom, certain dangers also lurk. You'll never know when you'll meet the dreaded ping of death. A special version of a normal request ping, which some idiot thought up to mess up unsuspecting hosts. The paths our packets take may be via satellite, telephone lines, wireless, or even transoceanic cable. They don't always take the fastest or shortest routes possible, but they will get there. Eventually. Maybe that's why it's sometimes called the worldwide wait. But when everything is working smoothly, you can circumvent the globe 5 times over at the drop of a hat. Literally. And all for the cost of a local call or less. Near the end of our destination, we'll find another firewall. Depending upon your perspective as a data packet, the firewall could be a bastion of security or a dreaded adversary. It all depends on which side you're on and what your intentions are. The firewall is designed to let in only those packets that meet its criteria. This firewall is operating on ports 80 and 25. All attempts to enter through other ports are closed for business. Port 25 is used for mail packets, while port 80 is the entrance for packets from the internet to the web server. Inside the firewall, packets are screened more thoroughly. Some packets make it easily through customs, while others look just a bit dubious. Now, the firewall officer is not easily fooled, such as when this ping of death packet tries to disguise itself as a normal ping packet. Okay, well, it's okay. No problem. Stay. We out of here. For those packets lucky enough to make it this far, the journey is almost over. It's just a lineup on the interface to be taken up into the web server. Nowadays, a web server can run on many things, from a mainframe to a webcam to the computer on your desk. Why not your refrigerator? With a proper setup, you can find out if you have the makings for chicken cacciatore or if you have to go shopping. Remember, this is the dawn of the net. Almost anything's possible. One by one, the packets are received, opened, and unpacked. The information they contain, that is, your request for information, is sent on to the web server application. The packet itself is recycled, ready to be used again, and filled with your requested information. Addressed and sent out on its way back to you. Back past the firewall, routers, and on through to the internet. Back through your corporate firewall. And onto your interface. Ready to supply your web browser with the information you requested. That is, this film. Pleased with their efforts and trusting in a better world, our trusty data packets ride off blissfully into the sunset of another day, knowing fully they have served their masters well. Now, isn't that a happy ending?
All right. I really like playing that video. The first time I saw it was in my A plus class. My A plus teacher played that video. This video is a very old video, as you could probably guess. And when he played the video, it was like it really put together all of the little pieces that we had learned about networking in the A plus class. And it was like, oh, I get it. You know, the concepts they attack the concepts playfully, but at the beginning of networking, you really need to have an overview of the concepts before you get into the nitty gritty. Because if you're in the nitty gritty, if you're in the weeds trying to understand how to do a host name and assign an IP address to an interface, and you don't understand why you're doing it, then it'll be much harder to understand the concepts. All right, now there's another video here talking about how devices in a how individual devices see the internet, and this is from our NetAcad content. Again, it's on that itanswers.net website I told you a few minutes ago about. If you don't have it, if it doesn't sound, you can play it there. But I'm going to play it now. Hopefully the sound is okay for you guys.
This is how we see the network. Using topology diagrams, we can see the devices in the network, including end devices, such as desktops and servers, and intermediary devices, such as switches and routers. These diagrams may also contain detailed information about a device, such as the MAC address of the Ethernet and wireless NICs, IP or Internet Protocol address information, default gateway addresses, and addresses for the DNS server. By the way, don't worry about what these terms and addresses mean right now. All of this will be explained throughout this course. This is how we see the network. But how do devices see the network? You can think of it as every device being in its own bubble. The only thing a device knows is its own addressing information. In other words, this is how a device sees the network. It doesn't. So, how does a device know its IP address and what network it belongs to? How does a device know if the destination device that it needs to send information to is on the same network or another network? If the destination is on another network and the information has to travel through intermediary devices, how does the source device know where to send it next? How does the source device know if the information it sent was received or if it needs to resend anything that might not have reached the destination? The answer to all of these questions is protocols, the rules that govern how devices communicate. Most network communications are broken up into smaller data units, which we can refer to as packets. When packets are sent on a network, many protocols are involved to help them reach their final destination, each accomplishing a different task. There are protocols such as Ethernet and wireless protocols that physically connect the device to the network. The protocols DHCP and ICMPv6 provide IP addressing information, including IP addressing that tells the device what network it belongs to, the address of the default gateway that tells the device where to send packets that are destined for another network, and the address of the DNS server for when a device knows the domain name of a destination but needs the destination's IP address. For instance, when a user requests a web page from a web server, such as www.example.com, the device asks the DNS server for the IP address of the domain name www.example.com. IP is used to deliver the packet from the source of the information to its final destination, in this case the web server, similar to sending a letter. The web server will then respond back with a requested web page. TCP is a protocol used to guarantee reliability. In other words, to make sure all the information that was sent was received, such as the information that makes up the requested web page. If any of the IP packets don't make it to the destination, TCP resends them. So although we see the network like this, remember, it's a combination of many different protocols that allow devices to really see their place in the network and how to communicate with other devices.
Okay. Communication fundamentals. Networks can vary in size and complexity. It is not enough to have a connection. Devices must also agree on how to communicate. There are three elements to any communication. There will be a source, that's the sender. There will be
I don't hear any
Doc.
audio.
I'm not sure why we lost sound just there a moment. I apologize for that. Let me go back to the previous screen just to make sure I covered that material. So we use, when we talk about communication, there's three elements. There's the source, that's the sender, the destination, that's the receiver, and there's a channel, that's the media. Now this actually applies to human communication if you think about it. We have a sender, that would be the first person, and they transmit using their mouth or a phone in today's world, sending a text message or something. Then there's some sort of media that would be airwave, sound waves over the air, or it would be digital signals from your phone through a cell tower, for example. Then there's the receiver. That's the other person, or in this case, or a device on the other side, the other cell phone. And then ultimately, that's the messenger. The message, it gets decoded, and you can hear that message. Now, computers the same way. You have the sending device. It gets encoded. That's what we're going to talk about in a little bit. It passes over the medium, and then it is received on the other end. And on the other end, it is decoded, and then you receive the message. You receive the web page, for example. The rule establishment. The reason why we need rules is because without rules, it becomes difficult. For example, if you try reading this paragraph, it's hard to read because it doesn't follow the standard formatting that your English teacher taught you in 3rd grade. On the second paragraph, much easier to follow because you understand the rules. Well, same thing with the computer device. Also, protocols must account for the following requirements. They must identify the sender and the receiver, the common language that is spoken and grammar, and if we have a written item, speed and timing, and confirmation or acknowledgement requirements. Now, we're going to use the example of a letter traveling through the mail system throughout today's presentation. At this point, we just talk about how the sender and the receiver are identified on that letter, right? And then you put it in the box and then off it goes. Now, what happens as it's traveling, post office has its own protocol about how a letter gets from one place to another. We'll talk about it. Now, network protocol requirements. Common computer protocols must be in agreement and include the following requirements. The message has to be encoded. The message formatting and has to be formatted, and there has to be encapsulation. The rules are applied to the size, timing, and delivery option of the message being sent. Now, here they show that the encoding process, and the encoding process is the process of converting the information in an acceptable form for transmission over the medium and ultimately to be decoded on the other side. So here you have a source and is a computer, and it has a message, your request for a website, and then it is encoded. We'll learn about that as we move through the course. It's transmitted across the medium. That medium can be copper wires, electrical energy. It could be fiber, that would be light, and it can be wireless, so it could be RF. So it has to be transmitted in the right form to travel the medium, and then medium. And then on the other side, it has to be received, and it has to be decoded. And that decoding, it turns it from electrical signals to a digital signal that the receiving device can understand. It's decoded, and then the website, for example, is on the other side. Now here, the same thing happens in the other direction. The message is decoded. Once it's changed, then it's sent read. Then say if you're requesting a website, that message then is re-encoded and sent back the other direction through the same process at the top. Now, when you're sending a post office letter, you write your letter in an agreed upon language, and you put it into a format that can then transmit through the network, the post office in this case, in a way that the post office can understand it. In this case, you have your letter, and then you go from sender to receiver. The sender is always in the top left, the receiver is always in the bottom, and then you have some sort of stamp. Now, that should be obvious to most people, but my wife doesn't really understand this concept very well. She'll chicken scratch the destination and the receiver, and she says, oh, the post office just understands. But they don't. For example, in my wedding invitation, several people, including people in my own family, did not get the wedding invitation because she chicken scratched not only where it was going, but the return address. So the post office got that letter, and they had no idea not only of where to send it, but not where to read it. You don't write in script generally on a letter unless you have really nice, neat script, and my wife does not. So you need to follow the format and make sure that it is legible. Just like in a network, you have to make sure you're following the rules. And the rules have, for example, this is an IP address, and it has specific fields, and the specific field is the source, where the address is where the message is coming from. where it's going to, the version IPv4, IPv6, and other things like how much data is in it and what the hop limp is. We'll learn this in detail as we move through the course. You don't need to know it now, but just know that a message, a frame traveling through the internet has specific information, the ones and zero, the order of the ones and zeros, because that's all this really describes is the ones and zeros and what order they're in. The first byte, this does this. The second byte does this, right? You have to. The computer understands that. Now, message size encoding between hosts must be in the appropriate format for the medium. Messages sent across the network are converted to bits. The bits are encoded into a pattern of light for fiber, sound for sound, which would be RF, I guess, unless they're still talking about you and I talking, and then electrical pulses if we're talking about copper. The destination host must decode the signals to interpret the message. So the message in here, they're just talking about a specific size. Sometimes you send a message and the OSI model actually, and the TCP/IP, the network actually can determine that the network size is too big and it has to break it up into smaller pieces and resend that message. Think about when you call somebody on the telephone, maybe a tech support person for a company, and you rattle off the technical solution for what's going on your computer and what you think the problem is, and you say, send me a replacement. I just had to do this with my hard drive not too long ago. Not my hard drive, my motherboard not too long ago. And the other side, I love ASUS. They're fantastic tech support. I highly recommend ASUS, the ASUS products. The tech support is second to none. It's fantastic. I had a motherboard that crashed 4 years and 8 months after I purchased it, and ASUS didn't even blink an eye, and they sent me a new motherboard. So I'm really high on ASUS, and I always talk highly of them. I can't say that about some other people, other companies, but your mom told you all, if you can't say anything nice, don't say anything at all. So I won't say those other companies that aren't so great with customer support. I know you guys know who I'm talking about probably, or you've run into bad tech support in the past. But anyway, so back to the conversation with the tech, when I call them, and not ASUS, they're fantastic, but I've called people in the past, and that tech support phone call, I'll rattle it all off, and then they'll say, oh, so you're having a problem with your computer. What is your name? And then you say, Don Lafond. They're like, could you spell that for me? I say, Don, L-A-F, and then they're like, no, the first name. What's the first name? It's D-O-N, and the last name, Lafond, L-A, and you end up slowing down to a crawl, because if that's what you need to do to get the message from point A to B, or from your side of the phone to the tech support side, if you have to say, I turned on my computer and it didn't work, right? If you need to slow down to that speed, then you need to do that. Just like a network sometimes has to slow down to be able to receive the messages. All right, flow control. And flow control manages the rate of data transmission and defines how much information can be sent and the speed at which it can be delivered. A response timeout manages how long a device waits when it does not hear a reply before it requests a new message to be sent. Now that's only with TCP. That's not with UDP. TCP will resend the message. Something like a web page, you want the entire website. Sometimes something like a file transfer or connecting to your bank, you definitely want a full connection of the data that's being transmitted. So you need to use TCP. Now, on the other hand, other devices like an IP phone call or a video played on YouTube if a piece of data isn't received, you really don't want that data to be played after or after it was. Could you imagine a phone call when if words just came out of place, or a website when you're watching a video and you would get the missing packets that would automatically jump into whenever they were received, or you'd be waiting forever for the data and it wouldn't be a very good experience. So they time out with TCP, not UDP. Again, we learned that later on. It's not in this module, but I thought I'd introduce it now. Access method, it determines when someone can send a message. There may be various rules to governing, such as collisions. This is when more than one device sends traffic at the same time and the device becomes corrupt. Some protocols are proactive and attempt to prevent collisions. Other protocols are reactive and establish a recovery method after the collision occurs. So, for example, collision detection, multiple, I always forget that. Hang on just a second. So I went ahead and modified my slide to add the information because I don't know how long I've been teaching Cisco for a long time. And sure enough, I always struggle with these two terms. I understand the terms. I know what they're used for, but I can get them in a multiple choice quiz, so we're good to go there. But Csma Cd, that stands for Carrier Sense Multiple Access with Collision Detection. Think about hubs. What happens is you have everybody transmitting at the same time, and they try to determine the collision, and then they'll set a timer, and then people send again based on a random send, so that they don't have another collision. And the other one is CSMA, Carrier Sense Multiple Access with Collision Avoidance. Think about wireless. When you transmit wireless, everybody gets that signal at one time. You don't have a direct connection to any device. So it's everybody is sent, but there is those devices, when they go to send back information, they may have collisions, and so collision avoidance is applied to ensure that there is no collision a second time, or at least it reduces the chance. So those are the two terms that I stumbled on just a moment ago, and they're easy to understand. We talk about them later, I believe, in this class, and I'll bring it back up with more details when we get to that point. Now, we also talk about message delivery options. So just like in the real world, when you're talking to people, you can talk to one person. That would be a unicast message. It's one-to-one communications. It could be multicast, and maybe you're just talking to a few people in a room full of people, right? Think about a party, and you're only talking about to 2 or 3 people, but yet there's 15 people in the room, or a classroom, you're talking to 2 or 3 people, but a whole room full of people, right? That would be multicast. And broadcast is you got that bullhorn, and you are screaming out to the entire room in a classroom environment, for example. They show a simple breakdown of this. So this is unicast. This is multicast. This is one-to-many, not usually all, but it could be all. The many could be all, but don't get confused by that. It could still be a multicast. And broadcast. When the multicast could be to all, maybe you're sending to all routers, for example, and you only have routers, so that would happen to be all in this case. And then they show you another way of looking at that same thing. So here we have unicast talking to one, multicast talking to some but not all, and then broadcast talking to all, and they call this a node topology. Protocols, 3.2 is protocols. So we need network protocols to define a common set of rules. They can be implemented on devices in hardware, software, or both. Protocols that have their own function, format, and rules, and each protocol is different. So we have network protocols. They can establish, they can enable 2 or more devices to communicate over 1 or more networks. Those are network communications protocols. Network security protocols, securing data to provide authentication, data integrity, and data encryption. Routing protocols enable routers to exchange route information, and they compare path information and select the best path. For example, OSPF, EIGRP, RIP, those would all be routing protocols. And service discovery, they are used to automatically in the automatic detection of devices or services. Now, we get deeper into all of this, so don't worry. Network protocols, that's devices need to agree upon certain protocols to be able to communicate. Protocols have one or more functions. So one function could be addressing, and that's what this little picture has here. So the picture shows that this guy is going to use IPv4 to communicate. These routers could be using EIGRP or OSPF, RIP to communicate with each other, but they also know IPv4, so that signal is sent to the server, and the server also understands IPv4 and can respond with the same protocol back to the sender. Now, the function also could be reliability protocols. They provide guaranteed delivery. That's at TCP compared to UDP that I was talking about earlier. Flow control, ensuring data flows at an effective rate. Sequencing, uniquely labeling each transmitted segment. Remember, I broke up one packet. I'm sorry, I broke up one stream of data into multiple PDUs that are then sent on down the. I haven't even talked about the OSI model yet, so we'll get there in a minute. Sequencing, so when you break a big file, let's say I'm sending JAWS. I have no idea why I use that example, but yesterday I used the example of sending the movie JAWS to a friend. I own JAWS, I own it on my computer, I send it to my friend. I'm not going to send that one big 750 megabyte file. I'm not going to send that as one file over the internet. I'm going to break that up into pieces, and those pieces are going to be uniquely labeled, the segments, each segment, so it can be reorganized on the other side. Error detection, if any of those individual pieces are lost along the way, error detection will determine that. They'll say, hey, this is corrupt, and if it's TCP, they'll ask for, TCP will just send again. And then application interface, it's a process-to-process communications between network applications. So I think HTTP on both sides being able to understand HTML. Protocol interaction. Now here's just an example as a layer. This layer it just has, in order to send a message from one computer to another, you have to have the web page, maybe TCP, IP, and Ethernet. This is the application layer all the way down to the physical layer, Ethernet. We'll get it deeper into it, but HTTP, for example, governs the way the web server and web client interact. It defines the content and format. Transmission protocol manages the individual conversations, provides guaranteed delivery. I've told you that before with TCP, and manages flow control. IP, that's all about addressing. We're IPv4, IPv6, and we'll learn all about that in this class. And then Ethernet, this is the actual NIC-to-NIC communication between either copper, fiber, or wireless media from one NIC on one device to another NIC on another. Protocol suites. Just like in communication, where we have to have a set of rules that allow us to communicate. In this case, we have the content, how to format the content, in this case, what the actual question is. In this case, it's where is the cafe? That is written in English, for example, and it's a sentence. And the way we say it, when we have a question, where is the cafe? We ask with a coming up higher on the last note. Anyways, there's a message there, right? And how we say it matters. Like, where's the cafe, right? That is different than, hey, where's the cafe? And then there's rules. It's the common language, wait your turn, signal when finished. And then the physical layer, that's actually the sound waves traveling through the air, or they're talking on a phone. It looks like one person's talking on a phone. So that would be how a device communicates through cell towers, for example. Now, higher layers, such as the content layer here, the application layer, they deal with actual communication and the interaction with maybe a human being. The lower layers, they're more concerned with moving the data and providing services to upper layers. Now, the lower layers, that would be ones and zeros, right? You don't want to be looking at a streams of ones and zeros at the physical layer to determine where the data is. Yeah, I'll stick at the application layer using HTTP or DNS or DHCP or FTP. That's where I want to be, not at the data, the ones and zeros layer. Now, the first model they show you is NITA. It's network access. That's the N. I is internet. T is transport, and application is the A. So you want to remember this as NITA. It's easy enough. Over time, you will get that pretty simple. And then there are this one. It's a open protocol. The most common protocol suite, and it's maintained by the Internet Engineering Task for the IETF. Now, there's also an OSI model that we'll get to in a couple of minutes. It was developed by the International Organization for Standardization, the ISO, and the International Telecommunications Union, ITU. There's also AppleTalk and Novellware for a couple more examples of suites. The good news is we don't need to learn these. We just learn about TCP/IP in this class, so don't worry about that. And we can see transport layer is TCP, UDP, application is, I already read those. Internet is the IPv4, IPv6, and then ICMP v4 and v6 as well for communication before devices. That's how you ping. Is through ICMP v4. I won't get any further than that. And network access, whether you're copper with Ethernet, ARP with communications, and wireless here as well. We'll leave that there. And then this protocol, the TCP/IP protocol, this model allows the communication to happen, the internet to happen between two devices, in this case a PC and a server, and all of the internet in between. This describes in a way that helps us to learn. It also describes in a way that allows the people that are developing the internet, the people that work on building routers and switches and other devices, it allows them to work just at the transport layer. So somebody could be working on how IPv4 and IPv6 work. It could be working just at this layer, etc., talking about those individual layers. Well, there's a slide that comes up in a minute. Now, this slide shows us the actual protocols that are used at each different layer. So right now, you may not know what all of these layers are, but yet in this class, we will go through every one of those protocols, and you will know not only what they are, but maybe even how to set up, in the basic sense, set up some of this stuff. The only one I'm not sure that we cover is REST, but DNS for servers and IT and mail protocols. I spent a whole day on this stuff, so don't worry about learning that now. Transport layer, again, TCP, UDP. TCP is connection oriented, which means you actually make a connection that then you wait for reply messages. UDP, it's connectionless. You don't wait. You just keep broadcasting, like FM radio. FM radio is not waiting for somebody to actually be listening to the channel, right? That's a good example of UDP in a different media, obviously, but UDP doesn't care. It just sends the message, and if somebody hears it, great. The internet layer, we have IPv4, IPv6. We'll learn about that. NAT is network address translation, and that is how we have private addressing in IPv4. We also have some more protocols that we'll get into. The routing protocols at the internet layer, layer 2, well, that's not, I really shouldn't call it layer 2 at this point. Layer 3, really, is OSPF, EIGRP. That's how we route and talk between different routers. Layer 2 and layer 3 is much easier to explain at the with the OSI model. So I'll wait and we'll talk about that in just a couple minutes. And then network access label, again, with address resolution and the actual protocols for sending Ethernet data or wireless data. All right. And then now the actual encapsulation and de-encapsulation. So a device has to encapsulate data as it moves down the OSI model and then send it across a frame across this cable, picture light if it's fiber, or ones and light if it's fiber, energy levels if it's copper, and those energy levels or light represent ones and zeros, right? So if you were to use Wireshark, for example, and listen to a stream of data, this is what you would pick up. And then Wireshark would have to interpret that so that you, if it wasn't encrypted, you would be able to take somebody's password if it was not encrypted, their login and password. But what that's beyond this slide's information. But going in one direction, it encapsulates. Going in the other direction, it de-encapsulates. And I have a video here that I'm going to play. Now, this video, I'm going to pause and pull it up. This video actually is from Astrid Carnici, and Astrid is wonderful because he set us up with this message heard around the world. He walks you through the encapsulation and de-encapsulation, but he does it in module 10 of the Cisco CCNA V5. We're on V7 with my presentations. But module 10, he wraps it all together and he actually shows you what we've talked about, or what he's talked about with all, there used to just be 10 modules, and what we talked about during those 10 modules. Now we have 17 modules or something like that. They broke it down. But at each layer, what happens in the encapsulation and what happens at the de-encapsulation. I really love this video. So I play his video. Let me open that up. And I want to give full credit. This is on the web. This is Astrid Carnici. That's his name up there, Astrid Carnici. He's a fantastic educator. He is really how I learned Cisco 1. I highly recommend him to taking you deeper into each of these concepts than I even go in my presentation. If you really want to understand the concepts, then go watch his videos. Now, they're not in the same order, like I just said. They're CCNA V5, but if you're talking about TCP, if you're talking about UDP and TCP, then go to that video that he has. If you're talking about if you're talking about IPv4, go to that video, even if it's not the module we're currently working with. It's still the same concept. Remember, the OSI and the NIDA, it just represents what happens in the internet. Whether you're using CCNA V5, V6, or V7, which is the most current, or V8, which is going to happen 2 years from now when I finally have my class all set up. They'll go and change it. Cisco will change it for one reason or another to make it better. And they do make it better generally. But the actual router, it's still a router. It still works the same. The actual switch is the same. It works the same. The protocols work the same. Although they can change, they basically are the same, or some of the minor things may change. the iOS might change a little bit, but we've been in iOS 15 for a number of years now. As long as I've been teaching, we've been in iOS 15. Who knows if they'll come up with something else after that. But anyways, let's watch the video so you can see what I'm talking about. And hopefully it will help you understand the encapsulation and then de-encapsulation and the PDU as it moves down the OSI model. Actually, he doesn't use the OSI model. He uses the TCP/IP model to move down the chain, and as it adds the name changes. The PDU is a PDU all the way through, but the name of the PDU changes as it moves down and then moves back up again. Here we go. I've talked enough.
Okay, thank you for watching my video. My name is Osi Reference. I'm authorized CCNA, CCNP, Cisco trainer. Now we're going to move to section 10.3, the message heard around the world. Now, what happens to the message when we send something on our network? We use a browser or email or FTP server. That message is going to go through the layers. At each layer, there's something going to happen. An application layer is going to identify what kind of message is it, what stream is it, how am I going to compress it, how am I going to format it, and so on. After the application layer is actually done with the stream, it's going to hand it over to the transport layer. Now, the transport layer, the message at this layer is called a segment. What the transport layer is going to do is going to take this message and it's going to split it on the different segments. While the splitting of the segments is going to identify at each segment with a sequence number. So each segment is split into pieces, and each piece is identified with a sequence number. The transport layer is going to add its own header. Its header is port addresses. So it's going to take the source port is going to take from private range. In this case, I've used 64,001, and then destination port 80. Now, port 80 is from the well-known range, which identifies that this message is the destination is some website or HTTP. For example, if we were using secure HTTP or HTTPS, the destination here would be 443 rather than 480. Okay, after the transport layer has finished adding his own header, it's going to pass it through to the internet layer. At the internet layer, it's called a packet now. Now, internet layer is going to add its own header. The internet header is the source IP address and the destination IP address. So the source IP address is 10.1.1.10, which is the client PC on the top, and the destination IP address 10.1.1.20, which is the server on the right. Now, this source and destination IP address, it never gets changed from the source to the destination. Doesn't matter how many hops it goes through, the source and destination IP address remains the same. After that, now it's called the packet. After the internet layer is finished, it's going to give it to the network access layer. At the network access layer, the name changes. Now it's called a frame. A frame, it adds the MAC address, source MAC address, and destination MAC address. Plus, it adds the frame check sequence to make sure that the frame has not been corrupted. The other side actually knows it's going to check the first thing, frame check sequence, and making sure that the frame has not been corrupted on the transit. Now, the source MAC address and destination MAC address would change from hop to hop basis. Okay, the network access gives it to the make sure they're all zeros and ones, and it passes it through the medium, and it goes to the destination. At the destination, it's going to do the reverse. While the client was packaging this with the different headers on the data, it's called encapsulation. Now, when it goes to the other side, to the destination is going to do something called de-encapsulation, which is going to mean that it's going to open and remove all the headers. Right, okay, let's go again. The other side. Next, it's going to go to the network access, open the frame, which is called now, and first thing it's going to do is going to remove the frame check sequence, making sure the frame has not been corrupted on the transit. After it makes sure that the frame has not been corrupted, it's going to read the source MAC address and destination MAC address. We'll find out the destination MAC address is itself, so it's going to pass it through upper layers now. Remove that portion, the header, and pass it to the upper layer. and it's going to reach the internet layer. At this layer is called the packet, and this packet is going to start reading the source IP address and destination IP address. Well, really just destination, making sure that it's for itself. If it's for itself, it's going to remove that header and give it up to the layer, which is the transport layer. Again, at this layer is a segment. So segment is going to make sure that, okay, this is the destination is 80, which means that they're talking about HTTP, and it's going to make sure that all the segments arrive, and it puts them on the correct order, and then give it to the application layer. Then the application layer is going to hand it over the stream to the destination. Okay, so this is how the packet travels from the source to the destination. When it gets to the destination, then the destination, if it has any messages to send back to the client, it will actually, the process will just be like the opposite, what we just saw. Okay, thank you for watching my video. This has been Astrid Krasniqi, and please have a look at my other videos, and don't forget to subscribe. Thank you very much. Bye-bye.
All right. Anyways, he does a.
Thank you for watching my video.
He does a fantastic job. These are the how he breaks down back in IPv CCNA v5. These are the way the chapters were laid out. So I highly recommend Astrid Krasniqi, and just jump to the video that applies, or maybe right before you go to take your CCNA exam, run through all of the videos. It will just be very enlightening. Again, I really liked him. There's other people that I like as well out on the internet for trainers, Jason Johnson for one, but I highly recommend Astrid Krasniqi, and you will too. You'll like him too, I bet. So here we go, and by the way, I just want to add, for the longest time, I struggled to remember at what layer these names came with, and then I learned that the frame, the only one that's not exactly easy, but it is an Ethernet frame, so maybe you can remember EF. But the frame has a frame check sequence. This is ones and zeros at the physical layer and the data layer. So frame is what actually is sent out over the internet. A packet, sometimes I make the mistake by saying we send packets, because ultimately the uneducated network person will say packets are sent over the internet, and they are, but they're actually they're further encapsulated at the data link layer. And I remember the packet is at the IP layer because it's literally in IP. So Internet Protocol, P is packet, I get that. The next one with segment, I remember that because it's ST. So it's the TCP layer, and it has a segment that's easy enough to remember. And then the user data itself is obvious. That's your data, and that's called a stream of data, and that's pretty easy to understand as well. So you need to remember what the PDU is asked, what the PDU is named at each layer of the TCP IP model, and then ultimately the OSI model as well. Anyways, you figure out a way for you to remember, but I remember frame easily. I just finally stuck, and then packet is in IP, and then user data is a stream. That just makes sense because it's a continuous flow of data, and then that just leaves segment, and I connect segment to TCP ST, and I'm there. So maybe that helps you. I don't know. Now, these are the slides I said that I was not going to spend a lot of time on. You need to know about each one of these organizations when you're out in the field, because you might have questions about the network or equipment that you're using, and you might want to research that information, and you would go to the appropriate organization to ensure that you have the right information. These organizations make sure that the standards allow for interoperability between vendors, competition, innovation. The standards organizations are vendor neutral, so Cisco doesn't own them. They're nonprofit organizations, and they're there to establish and develop and promote the concept of open standards. Remember, the United States, or whatever country you're in, does not own the internet. Now, they actually take the time to go through each one of these standards. You're going to do a lab that's going to actually explain, that you're going to learn about, and you're going to go through the content. If I were literally to read these things to you, it would really not help. You really need to read them on your own. And like I said earlier, make some flashcards to remember which organization is which. For the exam, the CCNA exam, or my exams there in the class, or when you go to get ready for the CCNA certification. Now, there are two reference models. We've talked about NITA, we've talked about the TCPI model already. Well, remember, the interoperability of equipment is the same. These protocols and how they work at each level, this is not tangible. The actual data is tangible. I guess you can touch the light, you can touch the copper cable. That's more tangible. You can touch the routers and the switches, right? But these are concepts, and the concepts explain how devices operate. Now, that's really important to understand, because when I first started learning this, I thought that I didn't really understand that this is just to help you understand the concepts. The network, the benefits of using a layered model to understand these concepts is that the concepts are complex to understand how the network operates. And so we initially used the TCPI PIP model, and then they decided that there was a better, we needed to break down the application layer into more layers to really explain what's happening inside of that application layer. And then even at the network layer at the bottom, there's a lot going on down there. So with the OSI model, they actually broke it down to 2 sections. So we went from 4 layers, if you will, to 7 layers. Now remember, I learned TCP/IP as NITA, and then I write that down, and then I know from bottom to top. So there's the way you learn about the OSI model from bottom to top again, it's please do not throw sausage pizza away. Please do not throw sausage pizza away. Now, that's critical for you to remember that. Write it down, practice it, understand it, because when you are taking your exam or quizzes here in this class, and you run into, it'll ask you at what layer does TCP UDP operate, and you need to know. It'll say the network layer includes which protocols, and it'll throw in several different ones, and you need to know that's IPv4, IPv6. And that's where, when you go to take your CCNA exam, they're going to expect you to know that. How you, which not, what do they call that? Which nomenclature's in my head, but that's not the right word. But that please do not throw sausage pizza away, whatever that's called. Somebody can throw that into the classroom. Whatever that's called, it's in an English term. I can ask my wife and she'll know. But anyways, that way to remember this group of terms in a specific order is really important. Now, there are other ways. I do not want you to blurt out what those other ways. There's one way that's really mnemonic, thank you. Thank you very much. A mnemonic is something that helps you to remember something else. And there's a way to remember this going in the other direction, the APST. I don't want to know it, because I know please do not throw sausage pizza away. 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 It's easy for me to remember, and you need to remember it. If you start throwing away, oh, there's one way to go up and one way to go down, you're just going to confuse yourself. So if you don't like sausage pizza, then maybe this isn't the right one for you. Maybe you want to go find the other one that goes APS and goes in the other direction, okay? Anyways, both represent the same network. The internet is and all the protocols in and all the hardware is represented in both of these layered models. The OSI model just breaks it down a little bit further, okay? So hopefully that helps. The benefits of using a layered model, well, it assists in protocol design because protocols that operate at a specific layer have defined information that they act upon and a defined interface to the layers above and below. How they connect to the layer above and below is defined at that layer. It fosters competition because products from different vendors can work together. It prevents technology or capability changes in one layer from affecting other layers above and below. And it provides a common language to describe networking functions and capabilities. Now, the OSI reference model, I'm going to go bottom to top. And this slide isn't fantastic. We're going to learn each one of these levels as we move through the class, but they try to sum an entire class that we're going to spend an hour learning on each one of these layers, at least one. We've spent 2 layers at the network layer for 2 classes at the network layer. They try to sum it in one sentence. So don't worry, you'll learn each one of these layers as we move through. But the physical layer, that describes the means to activate, maintain, and deactivate physical connections. Basically turn on that, the ones and zeros, right? How to put it on the fiber, how to take it off. That happens at and the ones and zeros being transmitted, the power to push the ones and zeros, or the LED flashing ones and zeros in fiber. The data link layer describes methods for exchanging data frames over common media. The network layer provides services to exchange the individual pieces of data over the network. That's IPv4, IPv6. Transport layer defines services to segment, transfer, and reassemble the data for individual communications. Remember that big Jaws movie that I wanted to send my friend? I have to chop it up and send it individually, and it has to get to the other side. The session layer provides services to the presentation layer and to manage data exchange. So it works together with the transport layer to make sure all the pieces are in the right order, and it can also break up the pieces. The presentation layer, that is great for common representation. It allows for common representation of data and transfer between application and layer services. At that layer, I think about the pictures, right? So pictures are formatted in JPEG, or they are in GIF, or they are in TIFF files. Well, a TIFF means something, and a GIF means something, and a BMP means something, right? Just like all the other formats, like MP3 for movies and MP4 for movies. MP3 for music and MP4 for movies. That's what happens at the presentation layer. Devices make sure that the packet is presented correctly, and you'll see. We'll get to that. We'll spend a week on it. And then application, that's the actual website you're looking, and it allows process-to-process communication. So you can ask for a website on one side, and you can be presented with the website that is on the other side, and it moved. That website request goes all the way down the OSI model, encapsulated, goes across, and then goes back up the other side and is de-encapsulated and presented on another computer as a website, for example. All right, and don't worry, like I said, we spent a week on each, so I don't expect you to learn from these single sentences that try to describe what happens at each of these layers. And the TCP/IP have the same explanation. So network access, that controls hardware devices and media that make up the network. That's actually a better definition than these two layers working together to do the same thing. This is like, hey, it's got to control how the fiber sends the ones and zeros across, how the computer sends, how the router sends the light signal across the fiber. That's at the network access. Internet, this is the best path. This includes TCP/IP at the internet layer. Transport, the transport layer supports communication between different devices across diverse network, and that is meaning that remember, you can have an Apple computer and you can send information to a PC, and it can because of protocols, the Apple computer will and should be able to communicate with a PC through the internet, and it does generally. I mean, Apple computers are kind of weird the way they do things, but I won't badmouth Apple on this video. They'll blackball me, and I'll never get anybody to like my videos ever again because of that. Apple people love apples, and that's okay. And then application represents the data.
Audio.
Don, you lost audio again.
I definitely think I have some motivation to fix this issue with my computers. It definitely has some sort of, it's either the fantastic $200 webcam I have, or it's some sort of conflict with USB. One or the other, I've got to figure this out, because I don't want my videos to be chopped up when I put them on YouTube. But fortunately for you, it only takes a moment for me to come back on, and I appreciate your patience with that. So anyways, so whether we're talking about, remember, whether we're talking about the OSI model or we're talking about the TCP/IP model, they both describe the network, right? The OSI model just divides the network access layer and the application layer of the TCP into multiple layers. The TCP/IP protocol suite does not specify which protocols to use when transmitting over a physical medium. And the OSI models 1 and 2 discuss the necessary procedures to access the media, layers 1 and 2, to access the media and physical means to send over data. So when we're, and we'll get into that, these are the physical, we're talking about, remember layer 2, well, you don't probably know this yet. Maybe you don't, maybe you do. But layer 2, that is our switches, right? And so that allows us to talk between, everybody talks within a network. That's a layer 2 device, that's a switch. A layer 3 device is at the network layer, that's IP. And that's what allows us for IPv4 and IPv6 communication between network devices in that internetwork that we call the web, routers and switches and other devices that are out there. So when you hear somebody talking about a layer 2 device, that's at this layer, a layer 3 device is at this layer, and yeah, and that's what they're talking about. So hopefully now when somebody's talking about layer 2, layer 3, it's generally, in this class at least, we're talking about switches and routers. Switches and routers, layer 2, layer 3, that's what they're talking about when somebody says it's a layer 2 device or a layer 3 device. You are going to do a packet tracer investigating TCP/IP and OSI models in action. Data encapsulation. So we watched the video about how data encapsulates. We're going to go a little bit deeper into that. Remember, I told you that we don't take just one file and we send that one big JAWS movie out over the internet. The reason why we don't do that is because this person, let's say this person is the one that's sending the file, this person would hog, if you will, all of the bandwidth while it's sending that 700 megabyte file through the internet. In the old dial-up days, that would have been excruciating for this guy to wait for that video. Now it'd be about a minute and a half over fiber, so it's a little bit easier, but still, this guy doesn't want to wait a minute and a half for that person to send a movie out to the server or download a movie from the server. So what we do is we segment. Segmenting is a process of breaking up the message into smaller units. Multiplexing is the process of taking those multiple streams of segmented data and then interleaving them together. So this person can be sending a movie in lots of little pieces over the same line that this person is sending web information and IP phone information, maybe watching a YouTube video. And they both can be acting at the same time because each one of these segments are labeled and they're interleaved with other types of data. So they're easily detected and reassembled on the other side. Sequencing message is the process of numbering the segments so that the messages may be reassembled at the destination. TCP is responsible for sequencing the individual segments. Now, remember, I already mentioned to you is as we move down whether we're talking about the OSI model or the TCP model, our PDU changes name, and I even gave you some help to remember when it's a segment, when it's a packet, and when it's a frame. And remember, at each stage in the process, the PDU is named differently to reflect its new function. Did you notice that the video that Astrid put had stream spelt wrong? He had it spelled AEM. I don't think I'll send him an email and tell him that. I think I'll just leave it the way it is. Maybe it's an English way or something of spelling that same word. There is no universal naming convention for PDUs in this course. The PDUs are named according to the protocols of the TCP IP suite. And here we see what those names are. And then encapsulation, I explained this to you with that video, it's a top-down process. It's encapsulated and then it's de-encapsulated in a bottom-up. We turn the ones and zeros that represent the encapsulated packet, a frame of information. It's broken down into a packet in a segment, and then the actual data that the presentation layer needs. Data access, well, addresses. Both the data link and the network layers use addresses to deliver data from source to destination. Network layer source and destination addresses are responsible for delivering the IP packet from the original source to the final destination. That would be the IPv4 and v6 that we learned in this class, IPv6, IPv4. That's at the network layer. At the data link layer, the switch layer, they're responsible for delivering the data link from one network interface card to another network interface card on the same network. So physical, the timing and synchronized bits, destination, data link, network, destination and source logical network addresses, transport, destination and source process ports, and all in an upper layer, that's at the actual stream of data itself. Now, these slides are really a little on the confusing side. So I don't spend a lot of time going through each individual one, but what I do want to explain to them, I can explain it on this one slide. So when you send a message to the server, for example, from one device to another host device, it has to go through the internet. When it goes through the internet, it has to have two things. The first thing, it has to have a source and a destination IP address. That is just like your destination and return addressing on the letter that you put in the post office. If you put a blank letter in the post office, it's not going to know where to send it. It's not going to know where to send it or where to send it back. Or like my wife's example, if you chicken scratch the destination and the return address and the hardware can't read it, then the scanners can't read it, then it's not going to go anywhere anyways. Or maybe you'll get it a month later if some person has to guess what the chicken scratch actually means. So source and destination addresses in IP on layer 3, they remain the same from the source as it bounces along the network. The source IP and the destination remain exactly the same all the way till the destination. Now, when it gets to the destination, if the destination is sending that information back to the source, they will reverse the source and information. So it will, as it moves backwards, it will, the new destination will be the original source, and the new source will be the original destination. That should just make sense. If your friend in California decides to write you back, they need to switch the source and destination. Both of those IP addresses, both of those physical locations will still be on the letter, but it'll be in different places. And that way the letter, you put it in the box, it comes back to you the next day because you didn't switch them. So you have to switch them, put it in the mail, and it'll make it home. Same thing is true with the IP. So that is this slide and this slide. And now, on the other hand, a NIC address, the NIC changes as it moves from source to destination. That's the MAC address. So let me get a slide that that works good for us. So this one. So as we move from the source, which in this case the MAC address is AAAAAA, through the internet, we are going to be using MAC addresses at the hardware NIC to know which device that we are going to. For some reason, they didn't enable the one in the middle, but let's just say this is 3333. So your device knows 1111. Your device only knows this router. This router, if it knows where this network is because of it's in the routing table, or because it just sent information back and it's in the routing table, I just said that, or because it's connected, like 2222 is connected to this network. So when it receives your packet, that bounces to 3333, it says, I don't know where this is. I'll send it on to my address of last return, my gateway of last return. I'm going to send it on here because I don't know what it is. It gets to this router 2222 R2, and R2 says, hey, I know where that is, and it sends it on. Maybe this router is supposed to symbolize the entire unknown network, where this actually happens over and over and over again. Until the hop limit is reached, your message, if it's going to an unusual destination, it will bounce around on the internet for a while until it gets to somebody that actually knows where that router is. I'm not going to get into that how it does that just yet. We'll talk about that addressing a little later. But what I want you to know is each one of these pieces of equipment have its own NIC address. So we don't, if it's on its own network through ARP, then it doesn't need to go out to the network. It doesn't need to use the network protocols like OSPF and EIGRP. It's not even going to be out here. It's just going to communicate within the network. It's just going to stay at layer 2. But if it goes out, if it needs to leave the network, then it's going to continue to use MAC addresses as it moves through the internet to get to the ultimate destination. All right, I'm going to leave it there and keep going. We'll talk more about it later on. And then when it gets to the other side, guess what? It's going to turn around and it's going to send those. It's going to send that information back in reverse, and this device will send to that gateway, and this gateway will say, I don't know where it is. Let me send it to my gateway. And this guy's like, I don't know. Let me send it to my gateway. And then this guy's like, hey, I know where that address is, and then it jumps over here. All right. Again, it says, while layer 2 local addressing will change from link to link or hop to hop, the layer 3 address remains the same. That sums it up. Hopefully, you can understand this concept without trying to understand these slides that did nothing but confuse me when I was learning the concept. I'd rather just teach you on one slide. If for some reason you think this is better, then you can go through these slides a little bit slower later and you can try to help it. I'll go watch Astrid Carnici and let him explain it. You just need to know layer 2, device to device, using NIC addresses, and they change every spot. Just like when you put that that letter in the mail. It has a source and destination that does not change. That's level 3. As it moves from your mailbox that you put it into to the post office on Main Street that has an address, that's the MAC address. It sends it to the post office in Delaware. That it picks up an airplane, it gets there by truck. That address puts it on an airplane. It flies out to California to an address or post office there on Broad Street. And then it changes from Broad Street to the final destination of your friend that you send that letter. Those are the MAC addresses. The physical address is the post office, just like it changes from along the post office protocol. It also, in the network, it changes the layer 2 MAC address from one hop to the next. Hopefully that helps. You're going to do a lab installing Wireshark. You're going to send me a picture of it installed on your computer. You are then going to use that lab to view network traffic. That is the end of our presentation. So hopefully you don't have a lot of questions, but if you do have questions, if you have any questions at all, other than why don't I buy another webcam, maybe I will, just see if it continues to happen. But if you have any questions, please, if we're together right now, you'll get a chance to ask those questions in just a moment. If you are watching as a recording inside of my NetAcad classroom this semester, then ask your question inside of the appropriate help discussion forum. We're in module 3, so you would ask a question in module 3. And if you are watching on the web using YouTube, please ask your question down in the comments below. I also appreciate any comments that you give, things that I can improve on. I definitely appreciate those as well. And I also appreciate if you subscribe and click that you like this link. That definitely helps to get more people to be able to see these videos that are now posted online. So again, my name is Don Lafond, Professor Don. Thank you so much for coming to class today. I really appreciate it. I will see you again in a future class, Module 4 next week. We'll see you then. Thank you so much.